In this video, we will start with chapter 5. This is permutation groups from the book. Now, before we go into the actual definition of a permutation, let's look at what you intuitively will think about a permutation. A permutation is, you will think about as a rearrangement of some objects. So, for example, if you have like a triangle, a square, and a circle, a permutation here will be reordering or rearrangement of this. It's going to be something like this. Now, that's the way you can think about it, and it is actually the correct intuition for the permutation. But here we're going to look at the formal definition mathematically, and then later I'll explain why this formal definition will actually agree with the intuitive definition of permutation. So let's look at the definition of what a permutation is. So a permutation on a set, so this is the set that's gonna be rearranged, is a function from the set into itself. So it's a function from A to A. The set A is what you're gonna do the permutation. That function has to have two properties. One of the properties is the function has to be one-to-one, and the other one is the function has to be onto or surjective. Now, those two properties that you see there, 1 and 2, these two things mean that the function is a bijection. That's the definition of bijection. Bijection means that the function is one-to-one and is onto. So whenever I talk about the bijection, I'm referring to a function that is one-to-one and onto. Now, if you don't remember the definition of one-to-one or the definition of surjective or onto, I'm going to recall that in this video. So let's look at that before we go on. So let's recall that. So a function is one-to-one. So I'm going to represent it by this notation. If the following is true. This statement. This is an if-then statement. So if this statement is true, the function will be called one-to-one. What is this statement here? So if you can prove that f of x, if f of x1 is equal to f of x proved, then x1 is equal to x2. That is for all the x1s and x2 in the domain of the function. If this whole thing is true, then we call that a one-to-one function. I will give you the picture of what this means in a second, but I want to point out first the formal definition. So whenever you want to check that something is one-to-one, you're going to assume that this is true for two particular x1 and x2 in the domain of the function, and by doing some argument, you're going to arrive that x1 is equal to x2. Let's see a particular example for this definition. So let's look at this function. So show that the function f, defined from the real numbers to the real number. So this is the domain, the inputs, and these are going to be the outputs. So the outputs are also real numbers, defined by this formula. F of x is 6x plus 4. So 6 times the real number plus 4, that will be the output of the function. We want to show that that function is one-to-one. And we're going to do that using the definition. So we have to check this property here. So how do we go about it? So you take two elements, x1 and x2, in the domain. In this case, the domain is the real numbers. And you assume that f of x1 is equal to f of x2. That's the statement that you have to assume, and this is what you have to prove. x1 equals to x2. So you start here, f of x1 equals to f of x2. Now, just use the definition of the function. F of x1 is just this 6x1 plus 4, which I have here. And this is f of x2 is the same function evaluated at x2. So let's just replace the x by x2 here. So that means these two things are the same. Now you can do some algebra here to check that x1 is equal to x2. So if you cancel out the 4 here, so 6x1 is equal to 6x2, and you can do the same with the 6. And so x1 is equal to x2, and that proves that the function is then one-to-one. So the function is one-to-one. Now, another way you can do this, which is not the preferred way. The preferred way is to do it this way, using the formal definition. Now, if you happen to have the graph of the function, if you know the function, the graph of the function, you can use the horizontal line test to check that is one-to-one. Now I have the function here, the graph 6x plus 4. That's our function. That's going to be a straight line that crosses the y-axis at 4. That's because this is the y-intercept and this 6 here is the slope of the line. Now the horizontal line test, what it says is if every horizontal line crosses the graph at most one time, at most once, then the function is 1 to 1. Now if you look at this graph here, this is a straight line. So every time you try to draw a horizontal line, it's gonna cross only at the one point, and that's gonna be true for all the horizontal lines that you draw in this case. So that's gonna check that the function is 1 to 1. Now again, I'm gonna say this again, this is not the preferred way to check that something is 1 to 1. What you want to do is go over this type of argument to prove that something is 1 to 1, but visually you can check that. Now let me emphasize a little bit more about the definition of this 1 to 1 here. Now if a function, I'm gonna say this again later, if a function is 1 to 1, so if you have, let's say, a b, and then we are representing this function by this kind of diagram. So here, this is the domain and this is the range. If a function is 1 to 1, what that means is this situation that I'm gonna draw is not gonna happen. So two inputs cannot go to the same output. So that's basically what 1 to 1 is saying for the function. So two inputs cannot go to the same output. So that's why when you say f of x1 equals to x2, if you have two outputs the same, they have to come from the same input. x1 has to be equals to x2. But again, you have to check all this formally. Now let's look at the definition of onto or surjective. So let's recall that. So that's what I said here. So this is 1 to 1. I'm gonna do that later. So that's what I draw over there. So that doesn't happen. All right. So let's go actually into the definition of onto. So we have again a function from a to b. We're gonna say that that function is onto or is surjective if for every element in the codomain here in the range, for every b in capital B, there is going to be an element in the domain. There's going to be an element in this domain, so that element f evaluated at a gives me exactly b. So graphically speaking, so if you look at this type of representation of functions, a function is going to be onto if I take an element in the codomain B, for every element that I take here, an arbitrary element, that a function is onto if I can produce an element in the domain A that maps to the element B. So that would mean that the function will be onto. So but the actual definition will be this here. So whenever you have to check that something is onto, you're gonna choose an element in the codomain in the range, and you're gonna prove that there is one element in the domain that maps into that element B. Let's look at an example here. So let's look at the same function. So let's look at the function from the real numbers to the real numbers that is defined as 6x plus 4. And let's check that that is onto. Now, so onto means, again, let me emphasize the definition one more time. You're going to take an element in the codomain here, and we have to produce an element here in the domain that maps exactly into B. So the way we go about it is, so we take an element in the codomain in the real numbers. So B here will be the real numbers, that's the codomain. We need to prove that there is a real number A, so that f of a gives me b. So we need to prove that. Now, we know exactly what the function does. F of any number, if we go back here to the definition, f of any number is 6 times the number plus 4. So I have to produce a real number here that's going to give me b. Now, what I'm going to write down right now is not going to be part of the argument. It's going to be part of what you do on the side to know what a will be. Now, I want to arrive to this one. I want to produce this A, that f of A is equal to B. Now, B is given to us. B is a real number. You have to find what A is. Usually A is written in terms of that number B. So let's do that. So what has to happen for f of A equals to B? Now remember that here B is given to us. Now what is f of A? Go back to the definition again of the function. That's 6x plus 4. So it's going to be 6a plus 4. So in this case, it will be 6a plus 4 equals to B. Now remember that the B is given and the one that you need to find is the number A. You can think about this one here as a way of knowing what A is. Because A is given, you need to find A. Then you solve for A there. So if you solve for A, 6a will be B minus 4, subtracting 4 on both sides, and then you divide by 6. So it's going to give you B minus 4 over 6. So this number right here will be the one that's going to be a real number, and that's going to give me f of A equals to B. Again, I'm going to say this again. This is not going to be part of the argument, the part of the actual proof. This is the one that you do to realize or to try to find what A will be. So in this case, A will be B minus 4 over 6. So you're going to continue the proof in this way. So the formal proof will continue like this. So B is an R. That's an arbitrary taken in the codomain. You have to prove this one. So the argument will continue like this. So we're going to take A to be defined as B minus 4 over 6. And that is, of course, a real number. It's a real number. What is that important that I said it's a real number? Because it has to be in the domain. So that was BA. Now, I'm going to erase this part because this is not part of the argument. That was just part of the work that you have to do on the side to realize what A is. So I'm going to take that in there. This is in the domain. So let me emphasize that. That's going to be in the domain. So B minus 4 over 6 is a real number. So that's going to be in the domain. And now I'm going to check that this is true. So what is f of A? It has to give me V. So f of A is going to be f of B minus 4 over 6. But then you apply the definition of the function. The definition of the function is f of any number is 6 times that number plus 4. So it's going to give me 6 times the number, which is B minus 4 over 6, and then plus 4. And that quantity has to give me B. And it does, because if you go ahead and cancel things out, so the 6 here is going to cancel. So that's going to give us B minus 4 plus 4. And if you simplify again, that gives you B. So we were able to find an A, which is this one right here, that is a real number whose image, when you apply it, the function f, it gives you exactly B. That proves that f is onto. So the conclusion here is that f, let me write down the conclusion here for this particular part. So then f is onto or surjective. So that will prove the function is surjective. Now, after all we have done here for this particular example, the function that I just mentioned from the example, 6x plus 4, that function from the real numbers to the real numbers, is one-to-one and onto. So that will mean that the function is a bijection. By the definition of permutation, anything that is one-to-one and onto is a permutation. So permutation is a synonym for bijection, assuming that the domain and codomain are the same. So this is going to be a permutation of the real numbers. So you can think about the function 6x plus 4 as a rearrangement of the real numbers. All right. So let's look at a theorem, and this is going to connect this part of permutation. Is going to connect this with the idea of what a group is. So this is a theorem of discrete math, which I'm not going to prove. So this is part of the discrete math course, but I'm going to explain these several results that we're going to use here. So let's suppose we have three functions, f, g, and h. that are permutations on A. What I mean by that is you have three functions, f, g, and a, all of them with domain and codomain the same set, because for a permutation the domain and codomain have to be the same, and all of them are bijections or one-to-one and auto. So we have three bijections from the set A to the set A. Then the following things are true. If you take the composition, so this notation here is composition. Now this will be if you don't remember what composition is, this will be a good point for you to review that concept of composition of functions. So the composition of the functions f and g, that also goes from a to a. If you do the composition of this function with this function, it's going to give you also from a to a. That composition is also a permutation. So recall the composition is you do the operation of g first and then f. So you go all the way from a to a, doing the operation of g first and then f. That's going to be the composition. So basically what this part is saying, number 0, is that if you have a permutation and another permutation and you do the composition, the result is another permutation. Now another result is there is a special function that we're going to call id of a, and the reason for id is because this is going to be the identity function that goes from the set A to the set A, and is defined by this. The identity function evaluated at A gives you A. So basically this function is doing nothing. So you give it an input and the output is exactly the same as the input. That's for all elements A and A. So this is the function that does nothing. Now this is another result also of discrete math. If you have three functions, the composition is associative. So when you do these operations here, it doesn't matter where you put the parentheses, either at the beginning or the end, you get the same function again. Now because these are bijections, so if f is a bijection by discrete math, there is a function called the inverse. So every bijective function has an inverse. Not all functions have inverses. Some of them do not have inverses, but if you have a bijective function, it will have an inverse that we call f to the negative 1. This is just notation. This is not meaning 1 over f. This is the inverse of the function f. So the inverse of the function f is also a permutation. So if f is a permutation, the inverse is also a permutation. That's another result. And the last one is when you do the composition of f and f inverse this way or this other way, you will get the identity function. Now I'm gonna call out something that may be obvious or maybe it's not obvious. If you look at all these properties that are here, so if you take two permutations, the composition is again a permutation. There is a permutation called the identity that does nothing. The composition is associative, and every permutation has an inverse. And then you have this property here. All these properties 0 to 4 should remind you of the definition of group. Remember what a group is a set with an operation that the operation is close. So two elements of the same type, when you do the operation, will give you the same type. There is an element called the identity. That's going to be number 1. The binary operation is associative. Every element has an inverse. That's number 3. And number 4 is that's one of the properties of the definition of group. So these 4 properties should remind you of the definition of group. So that's something that I'm going to use a little bit later. So pretty much what we are saying in this theorem is this. If you look at all the possible permutations on a set A, all those permutations will be a group where the binary operation is compositional functions. I'm going to say that explicitly in a corollary in a little bit. But before that, I'm going to use a little bit of notation. So if you have a set that is not empty, we're going to denote by S sub A, this is a sub-index, the collection of all the permutations on A. So this is the collection of all the functions from A to A that are bijection. We can express that a little bit formally like this. What is S of A? It's a collection of all the functions from A to A. So that function is a permutation or is a bijection. I can change this by bijection as well. So all the functions from A to A that are bijections, we're going to denote that by S of A. Now the corollary is what I just mentioned earlier, is this. If you have a non-empty set, this collection of functions, all the permutations on A with composition of function is a group. Why is that a group? How the proof of this goes, just refer to the previous theorem, which is basically saying all permutations with the binary operation being composition gives you a group. So that's why this chapter is called permutation groups, because it's talking about this type of groups, the groups that are functions on a set A that are bijections, and the binary operation is composition. Now we're going to simplify a little bit the notation. When the set A is the numbers from 1 through n, so it's this collection 1 to up to n when n is a natural number, instead of saying S of A, we're going to denote by S of n. This is just to simplify the notation. So this S of n here really means all the functions from this set to itself that are permutations. So let's emphasize a little bit that notation. So let me use the notation. What would be S of 2? S of 2 is S of A, but what is A here? A here is the collection 1, 2. So what will be S of 2? S of 2 will be all the functions from 1, 2 through 1, 2. This is the set A, where this function is a bijection. Now in this particular case, let's try to find all the elements in S of 2. So what are the elements in there? The elements are going to be functions. So let's find out the elements of S2. So again, this is going to be a group, and we're going to talk about this a little bit more in detail. For now, let's just look at just the elements of this group. Now, how do you define a function here? So a function goes from 1, 2 to 1, 2. Defining a function is knowing where 1 and 2 go, the elements. So I have to give input and what is the output. Now, this has to be a bijection. So whenever I assign the number 1, I have to make sure that it's going to be 1 to 1. So it's not going to go to the same, the 1 and 2 cannot go to the same element here. So they have to go to different elements because the function needs to be 1 to 1. So let's see the first possibility. So 1 can go into 1 or 2. Once I pick this number, that's going to restrict where I can send this number. So 1 could go, for example, into 1. And once I make that choice, the number 2 could only go into 2, because if 2 goes to 1, the function will not be 1 to 1. So 2 will go to 2. So that will be one possibility. 1 goes to 1, 2 goes to 2. So in other words, what I'm saying here is the identity function. This is the identity. Why is this the identity? Because it doesn't do, the function doesn't change the values of the input. You give it an input 1, it gives you the same output. Input 2 gives you the same output. Now there's another possibility here, and the other one, let's see, 1 here, this number, that could go into 1, but if I do that, it will give me the same function above. So let's do the other choice. It's going to be 1 would go into 2, and once I choose the value for 1, 2 will not go into 2 because it won't be a bijection, so this will be the other possibility. Now if you look at what we just did here, these are the only functions that you can get from the set 1, 2, and to 1, 2 that are bijections. So there's no more bijection. So S2 has only 2 elements, and the elements are this function and this function. Later, we're going to see a little bit better way to find all the elements of a particular Sn, and we're going to count them. How many are there and how to describe them a little bit better instead of doing this type of notation. So this S2, which is all the functions from 1, 2 to 1, 2, it has only 2 elements. One of them is the identity, because it has to be there because it's a group. And it has one extra element, which is this one. That is the function that takes 1 into 2 and 2 into 1. So that would be all the elements of S2. Alright, so that's all I have to say for this video. In the next video, we'll continue with more examples and more results about the permutation groups. Okay, that's all for today. Take care and good luck.